So the implications of activity are wide-reaching. They literally extend to every equilibrium reaction and expression that you've ever learned and that you'll ever learn going forward. So it's a fairly disruptive idea because it really tells you that everything you've thought of before this in chemistry has been relatively simplified, and things get much more complicated as the nature of the solution approximates reality, which means there's other stuff that's there, not just the thing we're thinking about. And so, of course, that extends to pH, right? Because pH is thinking about the negative log. It's a measure of really how much hydrogen ion we have in solution, dissolved in solution in water, and it tells us that the pH is equal to the negative log of hydrogen ion concentration. But I put this sort of squiggly line here because this is an approximation. And that can be a little unsettling, right? Because you're really used to this notion, but it's no longer apparently true if you don't have a solution where the ionic strength is 0. This is still true if the ionic strength is 0, but that's almost impossible. It's almost impossible to have nothing else in solution but pure water. So what that means is that pH is really the negative log of the activity of hydrogen ion concentration, which goes to say that's the negative log of the concentration of hydrogen ion multiplied by the activity coefficient of hydrogen ion. That's the true representation of pH, where we're taking into account what else is in solution and the impacts of the ionic shielding from the ionic strength. So the other question is, well, which do you measure, right? So if you've got a beaker and in that beaker you've got some solution and you pop in your pH probe, right? And that pH probe wires out and you've got a nice display here and you calibrated this thing and it says that it's 6.52. What are you measuring? What exactly are you measuring? Are you measuring the hydrogen ion concentration, meaning you're measuring actually the pH negative log of hydrogen ion concentration, or are you measuring the activity? You think about this. Does this electrode know any different based on what's impacting it? We'll talk at the end of this class, we'll talk exactly how these electrodes work. But you've got a hydrogen ion solution. Is it measuring the naked hydrogen ion, or is it measuring the hydrogen ion in the presence of other ions? In other words, it's measuring the apparent concentration of hydrogen as impacted by ionic shielding. Take a second, pause the video, really think this through for a second. Hopefully you concluded that it's measuring the activity, right? The activity is the true representation of the apparent concentration as impacted by a non-zero ionic strength. How many of those hydrogen ions are actually available to be measured is going to be a function of, well, whatever else is in solution. So how do we compute the actual pH of a solution, especially when it's in the presence of another salt that is not contributing hydrogen ions or hydroxide ions to solution? So very similar to what we've done before. So what happens when mu is not 0? So the example I want to look at is how do we compute the pH and the hydrogen ion concentration with 0.05 molar lithium nitrate in solution. And so first place we would start would be to determine exactly what is mu, what's the ionic strength of the solution. And so I can do this pretty quickly in my head because both of these are a +1 and a -1, and remember mu is equal to 1/2 the sum of those concentrations times their charges. As long as those charges are +1, then what we're going to get out is a mu that's the same as the original concentration. So our mu is 0.05 molar. So we could use that table that I mentioned in the previous video, or we could compute it using the Debye-Huckel. I'm going to skip over that because that's just algebra and it's not important here. But if you do that, what you'll get, at least if you use the table, which is what I did really quickly here, is an activity coefficient for hydrogen ion at 0.05 molar that's equal to 0.86, and you get a hydroxide ion activity coefficient that's equal to 0.81 in this case. So of course we're talking about the auto dissociation of water here. And so that has an equilibrium constant that we call Kw. So Kw is going to be equal to the product of the ion concentrations H plus multiplied by the hydroxide ion concentration. But as we know, we have to adjust this for the activity, meaning we have to multiply each of these concentrations by their activity coefficient, which we just grabbed from the table. So that means that Kw here, which is equal to 10 to the minus 14 at 25 degrees C, is going to be equal to the concentration of H plus times the activity coefficient multiplied by hydroxide concentration multiplied by its activity coefficient. So I just rearranged this in collected terms here. So I just substituted the values for our activity coefficients here into the expression that we just used, and then I just divided them into the 10 to the minus 14. So what we're left with is an expression that looks like this. So we have the original Kw now being corrected for or divided by the activity coefficients, that being equal to the hydrogen ion concentration times the hydroxide ion concentration. So in effect, we've calculated an adjusted or an activity corrected Kw value. So what does that equal? So you can compute that on your own. You'll get a number where the adjusted Kw, remember the original Kw was just 1.0 times 10 to the minus 14, but our new value for Kw is 1.4355 times 10 to the minus 14. So we've changed that actually considerably by about 50% change. That's significant simply because the apparent concentrations of both hydrogen ion and hydroxide ions are considerably lower when you have lithium and nitrate in the solution. So what does that mean? And there's a couple implications here, right? One is we can now just solve directly to get what the actual hydrogen ion concentration is, given we've already corrected our activity coefficient. So we'll do that here in a second. We'll compute that because that was one of the questions we were being asked in the original question, now that we've adjusted this. The other thing which I find to be kind of mind-blowing is the pH scale itself is 0 to 14 because of the fact that Kw is equal to 10 to the minus 14 at 25 degrees. And so what you've essentially said is that in the presence of other ions in solution, you have changed the actual pH scale itself. And so the pH scale is not a fixed notion. It is a function of whatever else you have in solution. More specifically, it's a function of the ionic strength. Even more specifically, it's a function of the activity coefficients of hydrogen ion and hydroxide ion in the presence of whatever those other ions are. That's a pretty huge implication in terms of my way of thinking, right? That changes the apparent sort of definitions for how I think about acids and bases. Maybe not hugely, but pretty significantly, right? Because this is about a 50% increase. I mean, it's a 43.55% increase from what we started with. So that's substantive. So I just quickly computed H plus from this expression. That's 1.19 times 10 to the minus 7, those digits being insignificant here for keeping sig figs. Of course, sig figs are important. Error is important when we're dealing with activity because sometimes the activity is on the order of the error or the measurement magnitude error, so it may not have a substantive impact relative to how we might measure it. But you know that the hydrogen ion concentration, if we assume no KNO3 or lithium nitrate is present, is going to be 1.0 times 10 to the minus 7. So that manifested in about a 20% increase in concentration simply because of another salt being dissolved in water. We can also just solve, we could have solved for this before we corrected the Kw, or now that we have the new hydrogen ion concentration that's been corrected for ionic strength, we can plug that back into the expression for the activity of hydrogen ion along with the original activity coefficient for hydrogen, which was the 0.86 value, and we could solve for what the activity of this would be. So this would be 1.19 times 10 to the minus 7 molar times the 0.86, so 86% of that gives us a value of 1.02 times 10 to the minus 7 molar. That's the apparent concentration of this species, not the true concentration. And remember, the apparent concentration, or the activity here, is the thing that you actually measure. So if we want to compute the real pH, that's going to be minus log of the activity of hydrogen ion, which will be minus log of this value. So we'll plug that in there, and that gives us a value of 6.99. Of course, this depends on how many sig figs we had going into this thing. So if we kept 2 sig figs, which I don't know, it looks like we probably have 2 sig figs. I don't know why I wrote this. This is probably actually 1.19 here, which means 2 sig figs, 2 sig figs. And remember, at this point, since we took negative log of this in terms of sig figs, this 6 is just a placeholder for zeros. And so the sig figs are only applied here, and so this is our value. So how does this compare? Well, I mean, it's not so dramatic, but we're also consider we're in log scale, right? So it's going to be less apparent on the log scale than it would be on a linear scale, because on a linear or on a log scale, the comparison here, if we didn't have lithium nitrate, would be 7.00. On the log scale, it's 6.99, which you may not even see if you didn't preserve significant figures, because this is going to round up to 7.0 pretty quickly. But this was with a fairly low concentration of lithium nitrate, so it does inform us that pH is not absolved from considering activity. And in certain circumstances, when you have really high concentrations of salt and you're trying to measure the pH of a solution, if you are simply calculating pH as the negative log of hydrogen ion concentration, but you're measuring negative log of activity of hydrogen ion, which is the sort of corrected concentration, those two numbers are going to be very different from each other. The thing that you measure versus the thing that you compute if you don't consider your activity. And so it's really important, especially if we're talking about constructing big models of equilibria, right? And this is hugely important in environmental chemistry, especially as a lot of the chemistry is done in oceans, especially as we think about ocean acidification and the impacts of global climate change. Oceans are really, really concentrated. Not only is there sodium chloride there, but there's virtually every element on the periodic table in some concentration in our oceans, meaning the mu for an ocean, the ionic strength for oceans, is quite high, which means the pH is quite a bit lower if we consider only the activity than what we would compute simply only considering the concentration. So there are huge effects on that. And so all actual models of equilibria will always consider activity in their models. And we'll talk about the impacts of this on the Flint crisis, because it becomes fairly apparent.